Okay, thank you. So I guess it lost focus or something somehow. Okay. So let's start before we lose momentum. Okay, welcome everybody. Welcome to this fall distinguished Mani Al Bhaumik lecture in theoretical physics, and I would like to thank Mani Bhaumik for his support that makes this possible. And the purpose of these lectures is to bring distinguished speakers to our department, and in the spirit of the great pleasure to welcome Cumrun Vafa. He is visiting us from Harvard, where he's been since 1985, and he's currently the Hollis Professor of Mathematics and Natural Philosophy. Cumrun is famous for his many groundbreaking contributions to string theory and to the associated mathematics that is needed for that subject. And his achievements include, among other things, the first calculation of the Bekenstein-Hawking entropy of a black hole from string theory. He's won many, many awards, more than I can safely enumerate. And so let me just briefly mention the Dirac Medal, the Heinemann Prize, and the Breakthrough Prize in Fundamental Physics, along with election to the National Academy of Sciences. And today he will tell us about new ideas that link string theory with particle physics and cosmology. So please join me in welcoming Cumrun Vafa.
Thank you. Thank you so much for this kind introduction. It's a great pleasure for me to be here and talk about connections between string theory and the dark sector. I will not assume any much advanced knowledge here, so I apologize to experts in the audience, but I think it'd be good to take the common ground. So I will start with the basics. In 1915, famous period where Einstein formulated his theory of relativity, and he wrote his famous equation relating curvature to the energy momentum tensor. And in particular, the left-hand side of the equation was telling us something about how the space-time is curved, and the right-hand side was telling us the impact of matter, which gives rise to energy and momentum. And basically, this equality connected the relation between these two entities. All was good, but not really. He soon discovered this doesn't work. And the way he thought about it, that he thought the best version of this theory is that it has to apply to the whole universe. And so he wanted to have a nice model of the universe, and the nice model he thought about was a round sphere, three-dimensional sphere in that case. But he found that just in that context, the fact that there is matter just collapses the universe on itself. It pulls itself back to nothing. And this seems to be inconsistent with what he thought at the time, where all the stars and all that, they were seeing that nothing seems to be moving and look static. So this didn't quite work. As far as he was concerned, he needed something to stop this collapse. So what to do? Well, he found that if you basically add something there to kind of balance the curvature and matter, he introduced this other term. This was in 1917, 2 years later. So he found that if he does that, it balances the curvature and matter perfectly. So you get a static three-dimensional sphere right there. And he said this might be our model of the universe. And this extra term that he added, which was there to fix the problem of cosmology, he called it the constant of cosmology, or cosmological constant. So this was a happy period. The equation still worked. It was a natural term, and therefore everything for him was pretty good at that time, until not too far from here, Edwin Hubble came and did some other observations, and he found that indeed the universe is expanding. Now, famously what he did is to discover that there are other galaxies besides our own galaxy, which was not known at that time. And moreover, he found that the farther away galaxies seemed to be going faster away from us by looking at the redshift that he was measuring. So this relation between distance of the galaxy and the redshift suggested that the speed was going faster away from us the farther away it was, and extrapolating backwards, it will give you that everything was together at some point, and now they're just kind of going away. And this was the beginning of the observational evidence for the Big Bang theory. So Einstein went back to his equations again in 1931. And he said, well, maybe I should not have added that term. He dropped the cosmological constant, said it was zero. And it turns out that if you do that, and if you don't put the universe on a sphere, if you just put it on a flat space, it kind of grows the way it was the Big Bang theory suggests, and everything is good again, consistent with observation and no extra term. So he was happy again, but nevertheless, he was not happy about the fact that he had to go back and forth with this. It's because he thought maybe he could have predicted that there was a Big Bang, basically by the fact that the static one doesn't seem to work. So, and he called this the biggest blunder of my life. So please notice that we went from lambda 0 to lambda not 0, back to lambda equal to 0. We're going to count what's going to happen throughout this talk. So let's continue with the historical evolution. At around the same time, quantum mechanics comes to the fore. Here famously in terms of discussions between Einstein and Bohr and other people who were developing the subject. The microscopic world was dominated by quantum mechanics. The atoms seem to need quantum mechanics to give you a consistent story. But Einstein's theory of relativity applied to universe as a whole and gravitational pull between any objects. And there cannot be two theories which are in conflict. There must be a way to put them together. And people tried to put them together, but somehow it seemed like it's very difficult to do that. Indeed, later on, theoretical physicist, famously Feynman, tried to really make sense out of the quantum theory of gravity, to combine gravity and quantum theory, as he had successfully done for quantum electrodynamics, where he had seen how the electricity and magnetism can fit with the electrons and the quantum mechanics all together very successfully. So he tried to do the same bag of tricks, apply it to gravity, and let it work the same way. So the same kind of diagrams that he was drawing for QED and so forth, he applied that for the context of gravity. And to his disappointment, he found that whenever he did this, he got nonsensical answers. He got infinities in his results. It didn't make any sense. So Einstein's theory seemed to be a bit inconsistent with quantum theory, and so that was a question, what to do. Towards the end of that same decade, late 60s and early 70s, quite accidentally, a number of physicists, starting with the work of Veneziano and some other physicists, which continued, noticed that a theory, this kind of contradiction between quantum theory and gravity can be resolved if you just postulate that fundamental entity of gravity, which we thought was graviton and a point-like object, is actually not point-like, but actually loop-like, like a string, like a loop of energy, vibrating string. Here, this is just a string which is vibrating in some mode. Now, this was a mysterious thing, but somehow replacing this point with one-dimensional extended object led to solving those inconsistencies that Feynman had in his diagrams. And the answers that they compute now in this theory, the string theory, ends up being finite answers again. The nonsensical answers disappear. So this became a theoretical evidence for string theory, basically as the framework which solves the problem of combining or making quantum theory work with gravity. It also furthermore leads to unification of all forces and particles as different vibrational modes of strings, could be different kinds of particles, and whether or not it's a closed string or an open string, and different vibrational modes could give you a plethora of states and particles, and they all fit together into describing things like electricity and magnetism, electron, quarks, strong forces, graviton. All of them could be packaged into the simple picture of a string vibrating, one string. Namely, the identity of the object is determined by the state the string is in, but not different strings. They're all the same string. So it was aesthetically beautiful. So it was aesthetically unifying all the forces, at least in principle it could do that, and at the same time solve the problem of quantum theory and gravity, putting them together. But there were some strange features to this theory, string theory, which kind of makes physicists a bit uneasy because you would like to see more evidence for it. This particular feature is existence of a requirement that there must be extra dimensions other than the 3 spatial dimensions and 1 temporal one we're familiar with for this theory to make sense. So it requires very specific features, which sounded strange. You need extra dimensions. How does that work? Well, and the way string theorists try to reconcile that with our observed universe, that we don't see extra dimension, was to say that these extra dimensions are basically these compact extra spaces, which is hard to detect. So at every point in space, imagine you have a circle or a bunch of circles, which are so tiny that typical experiments cannot resolve it. And so you cannot see this extra direction. Just like what would have happened if you have a water hose. It was very, very thin. From far away, it looks like a line, but actually it's two-dimensional, its surface. And you can only see it if you get closer to the object. Similarly, these extra dimensions could be viewed as something that you need to get close to see these extra features. So quantum mechanics leads to uncontrollable fluctuations of physical quantities and space-time itself. That's the feature of quantum mechanics. Things fluctuate. You cannot control it. It's the probability of different things happening is given by the action principle, and that implies that things are very dynamical. It's not frozen to be one particular state. So the space-time itself is kind of like bubbling at the microscopic level. But that actually leads to a strange feature. If you did this, you find that even if you start with the cosmological constant equal to 0, as Einstein had done, quantum fluctuations generated. It makes it non-zero again. So quantum theory seems to say no, even if you set lambda as 0, it actually is generated by itself and it's not 0. What is its value? Well, the naive value turns out to be, when you do the calculations in quantum mechanics, is of order 1 in the fundamental units of nature. So I have used what's called the Planck units. In those units, which are the fundamental units, where the Newton constant and Planck constant and the speed of light are set to 1, you'd expect the lambda in those units to be equal to around 1. But astronomical observations told us that this doesn't quite work. In fact, they found an upper bound of lambda to be less than 10 to the minus 120. 10 to the minus 120 was an upper bound for this number that was quantum mechanically expected to be of order 1. That was a disappointment. So something is strange there. So just imagine, just write this feature. If you see this thing, naturally, this led physicists to believe that it must be true that lambda is actually 0 for some good reason that we haven't discovered yet. And many people try to understand why. This attempt failed. String theorists, myself included, we tried very hard to find examples or symmetry principles of some kind which will give us that lambda should be 0 or could be 0. We not only didn't find why it should be 0, we could not even find a single case where it was 0 for which the universe looked like our universe. The only cases we could find it to be 0 was in a universe with supersymmetry, which is not our universe. So we could not find any examples in string theory where lambda could be 0. So naively, a string theorist would have said lambda is not zero because I can't get it to be zero. We didn't say that because we couldn't believe that lambda is less than 10 to the minus 120 and yet not zero. That was a mistake we made because Weinberg had a different view. In 1987, Weinberg suggested that if there are many different solutions to what a universe could be, if there are different possibilities for lambda for a universe, if a theory gives you any possible uses for lambda, the ones where interesting structure like ours can appear, like galaxies, are the ones that the cosmological constant cannot be too big. Because if it was big, it would blow away everything, and you would not get any structure form. For the structures to form, that lambda, which is the dark energy, which is like a negative pressure, should be sufficiently small so the matter could clump, form structures, and give rise to galaxies. If it didn't, no galaxy would exist, we wouldn't exist, and we would not be able to ask the question. So he said just the very existence of structures, our existence, and so on, presupposes that we would be in one of those kinds of universes for which lambda is not too big. And what is the value of lambda that could allow this? He found that lambda should be less than or equal to rho, which is the matter density in the fundamental units. And that was about 10 to the minus 120. So he found that actually the observations are precisely the upper bound that would be consistent with this kind of anthropic principle. Anthropic principle being that lambda is not fine-tuned other than its fine-tuning necessary for our existence of structure. So he said, well, maybe there's this principle that we can only look for explanation of things which we could even ask if we can assume the theory allows us to exist in the first place. And that would require lambda to be smaller than 10 to the minus 120. So he said, well, if the theory is not fine-tuned, we better be finding lambda pretty soon because that's very close to the observational bounds. Sounds like a strange prediction or methodology of prediction, but in one of the great success stories of modern times, this was discovered a few years later, less than a decade later, that indeed lambda is not zero. And this, I think, is probably, in my view, the most important discovery of the past, I don't know, 50 years or whatever. It's really amazingly affected a lot of things we think about. And we found that lambda is not zero. And the way they found it, this is by physicists Rees, Perlmutter, and Schmidt. And the way they found was that the radius of the universe, the galaxies, the position of the galaxies are expanding faster than polynomial. In fact, they're going exponentially expanding away at a rate which correlates with what would root lambda be. And the fact that they measured that there is actually this exponential growth, which was not consistent with the polynomial one that the Big Bang would have expected, led them to find the value for lambda. And the value they found was about 10 to the minus 122, very close to the value that Weinberg had suggested. Now, ironically, this is really strange. Ironically, Einstein's original model of cosmological constant also gave the lambda that he wrote was this formula, and his model, if you calculate, it's about the same. This is ironic. Now, this is ironic because it's accidental in a sense, because in Einstein's case, he was actually putting the universe on a round sphere. So he had curvature on it. Whereas we are putting the universe on a flat space where we think the curvature is very small or zero, and it's actually exponentially expanding. But somehow the value accidentally, ironically, is the same value you get, which is related to the density of the matter. Okay, so this is the history up to the turn of the century. Now, what is cosmological constant physically? Well, it turns out that you can think of cosmological constant as having the universe filled with an unknown source of energy everywhere, some kind of a source of energy. Now, in the context of the usual physics without gravity, absolute value of energy doesn't make any sense because we only talk about energy differences. That's what the potential energies and all that, only the difference matters, not the absolute value. But when it comes to gravity, the actual value also matters. And that causes the universe to expand. So the actual value of the energy matters. And you can think about lambda as a positive energy filling the whole universe. So imagine the whole universe has not a zero energy. It's not like in the ground state somehow. It's excited, it's somehow energetic there. Somehow there's some energy, there's some source of energy. And that's why another way of calling this has been called dark energy. And now I shift to a different matter called dark matter. So parallel to the, so keep on to the notion of the dark energy for a while until we discuss a little about the dark matter. We'll come back to dark energy momentarily. Parallel to this cosmological constant and dark energy, another puzzle came to focus originally by Zwicky in 1933 and by further work by Vera Rubin, culminating in her work in 1970s, where it was seen that if you look at the rotation curves of the stars in a galaxy, you find that the velocities that you get is not consistent with Newton's law if you assume that the matter you see is just the visible stars that you can measure. It works for a little bit, but if you go far away from the center of the galaxy, you find that there must be some other stuff that must be there that's invisible, that somehow causes the speed to be higher, namely this white curve, compared to the red curve, which would have been if there was no matter in the middle, where there was only the matter that you see. So this difference suggested that there is extra matter in the story, and it was not visible, and by that it meant it didn't interact much with the light, and you could have called it invisible matter or dark matter. And so therefore there must be some other source of matter if you believe Newton's laws or Einstein's theory. And so this is the prediction that there's other stuff in our universe, dark matter. What are the properties? What do we know about the dark matter? It interacts weakly, if at all, with known visible matter and light. Electrons, quarks, photons, and all that stuff basically do not seem to have much interaction with this. They are dark. No direct detection has happened for them. We cannot directly kind of measure them because it doesn't interact with stuff we are made of. So we know their existence mainly through their gravitational imprint, like the rotation curves in the galaxies is a gravitational phenomenon. It is an unknown kind of matter, which may be another reason we could call it dark. It's kind of our knowledge is not clear about what does this mean, so you can think of it differently if you want to think about the word dark here. What is this source of matter? It's more abundant than ordinary matter, about 5 times more abundant. And it's like a cold matter, not moving around fast. It's not like going fast like speed of light. It's basically cold. So you think about them as some cold stuff like dust of some kind, maybe, sitting around. It's not made of stuff we know of, and it doesn't interact much with us. It's just there. That's what we currently know about dark matter. A little more, but roughly these are the main features of it. So if you want to look at the energy budget in the universe, in this theory that we now are talking about, which is called the lambda CDM, lambda stands for the cosmological constant, and CDM stands for cold dark matter, which is now the standard model of cosmology, that you have dark energy and dark matter, which behaves like a cold matter. 68% or about 70% of the energy in the universe is the dark energy, or lambda. 27% or so is this cold dark matter. And about 5% or so is ordinary matter. We are negligible, in a sense, in the energy budget of the universe, at least at the level of 5%. Now, one question that's natural to ask is whether this dark part and this dark part are related. Are dark energy and dark matter connected in any way, other than the fact that they're both dark to us? In some sense, we don't understand them. Could they be actually related? Okay, so then I shift gear. So let me call the dark matter and dark energy, let me collectively call that the dark sector. Two things there. So what is the relation between string theory, which is this fundamental theory of quantum gravity, and this dark sector, dark matter and dark energy? Can string theory shed light on the dark sector? Well, how can the dark energy be realized in string theory? There are no free parameters in the theory. So what corresponds to cosmological constant? In this case, these extra dimensions that I was telling you, which was kind of a nuisance for us, could come to help, as I will try to explain. So think about extra dimensions of the space, parameterize the radii by some parameter, like the parameter I'm calling here phi. Think about phi as parameterizing the size. It could be that there's energy associated with what size you pick. So as you change the size of these extra dimensions, the energy could change in the universe. The energy that we observed in space, in the leftover space-time that we are in. So if we had a situation where the potential had a minimum equal to lambda, that means that you have this, think about this like an extra sphere or some kind of a shape that has a minimum, has a particular size which is stable. If you go a little larger, the potential goes up. If you go a little down, the potential goes up again. So there's some sweet spot where the energy is minimized. Then the value of the energy at that point could be lambda. That's what you would measure. So this would be one model that we could potentially get in string theory. However, it turns out that even though we have worked very hard, it seems to be very hard and perhaps impossible to construct such examples. When we tried to construct such examples in string theory, we felt unfairly difficult challenges arose, and we could not find a reliable example where all string theorists can feel like we understood the theory exists at that value with this stable potential. There were two problems for this. The value being small was a problem, as well as having a minimum was a problem. What frequent examples we could construct in string theory instead looked more like this. Instead of this, we would get potentials, which is kind of like a slope down somewhere, negative or positive. And if you wanted to find something like this in the middle, which what we call these kind of minima de Sitter spaces, even if we had such a thing, it would have been unstable to quantum tunneling and decaying outside by tunneling through that barrier. But we couldn't even construct one, really. So we were sure that these things, the potentials like this exist, but that would not give you a cosmological constant, because if you were here, it would start rolling. So therefore, we had been having great difficulty in string theory to come up with a model of lambda CDM. Now, I should add here that these regions where phi is large, the theory simplifies. The theory is easier to compute, and that's why we were able to do calculations here to find the nature of the V. When phi became small, it was corresponding to the space itself being tiny, and it's hard to get computations reliable at that region. So we couldn't do any reliable checks there. So we were kind of unable to do any calculations here. Whereas for large radii or large sizes, we could do the calculations reliably. And over there, we could establish that you never get a minimum. You never get a minimum. And these regions, what we call the weak coupling regions, because the theory was weakly coupled and it was easy to do the calculations. And these regions, as I say, correspond to the case where some of the extra dimensions became large, or maybe some strings became light. And we never got a minimum with a positive value. So therefore, we seem not to be able to realize the cosmological constant in this way. Phi, which is the extra dimension size, the radius, will start rolling. And so this extra dimensions will not be fixed. It will kind of wobble around and the shape of it will change and whatnot. But experimental bounds also told you that the slope of the potential is extremely small. Not only V was small, but the slope was less than 10 to the minus 122. Sounds like the same problem we were facing before. You remember we first found V was less than 10 to the minus 120 and string theorists were adamantly trying to show it's zero. And they failed, and the experimentalists came back with an answer that's not zero. Here, we know experimentally the value is less than 10 to the minus 122 of the slope. And guess what? We are trying to prove it's zero, right? What else could it be? We were looking for something which is zero with a local minimum and no rolling, of course. Actually, we thought that maybe we have learned this lesson once, so we should be careful about drawing that conclusion. So in 2018 and 2019, together with a number of my colleagues here, that are, whose pictures and names are here, we studied this more carefully. And we found in string theory, what seems to be the case is that the slope of the potential in these asymptotic regions I was showing you is always proportional to the potential itself, with constant of order 1. So the slope is almost like the value itself with a constant of order 1. In other words, just like an exponential function, exponentially dying function, with some exponent which is which is of order 1, the c. And we said, look, maybe this is not accidental. Maybe the reason we are not finding any solutions in string theory is that because this is a generic feature that somehow the slope cannot be too small. It can be almost as small as V itself, but no smaller. So we said, therefore, if V is small, then the slope is also naturally small. So we predicted that pretty soon we should find the slope of the potential is not zero, and it's not a cosmological constant, and it's rolling energy based on this observation from string theory. Now, this was very daring. When we wrote this paper, people called our colleagues in string theory, a number of them objected, saying you're basically saying string theory is false because the dark energy has been shown to be constant, so what are you saying? And so it was a very risky statement here. But the fact that we had a plethora of examples in string theory and none of them gave us any clue that this could be possible led us to make this conjecture. Of course, we couldn't prove this from string theory. It was very natural because it was all these models that were supporting this evidence. And the experimental bound was just around the corner, almost that value. So we said, if perhaps in the next round of experiments, this will be discovered. So we propose that in string theory, it's natural to expect the cosmological constant not to be a constant and should deplete over time. It should fade away. The dark energy should fade away gradually. This, from intuition, is kind of natural. If you have positive energy somewhere, you would think it's gradually going to die away. Why should it be excited from zero? That's roughly this picture. Now, then we continued further by asking, how about dark matter? What's the natural candidate for the dark matter in string theory? Well, then this we used another series of papers with the colleagues here. I've written their names here. which is related to what's called the distance or duality conjecture, which showed that whenever you have a large value of this field phi, you always find a weak coupling description of the theory involving either some large dimensions opening up, which give you a light tower of gravity excitations like these waves on it, like gravity waves in these directions. If you think about the gravity waves as just harmonics in these extra dimensions, and if you make the universe get bigger and bigger, the harmonics that you have will stretch and their energy will become down. It will go down because it's kind of stretching, and their mass will go down. So if you have a situation where phi is large, you always get a tower of light state, which are these harmonics, which are becoming lighter and lighter. So we said, oh, this is always true when you have extreme limits like phi. And so the parameters get, the dimensions getting larger will give you this light tower of particles corresponding to its gravity in these extra dimensions. So for large phi, we had the tower, not just one, depending on which harmonic you pick, you will get all these different states with lighter and lighter states, which are exponentially going down also. And when you calculate the slope of this function, you find again exponential function always, with some slope again of order 1 in this parameter, in this same field phi. Could these light towers be relevant for our universe? Could they be the dark matter? Now, to connect it to the dark matter, we have to be an extreme limit. But lambda, being so small, implies that there is a light tower, as I just said. And therefore, it predicts that there could be a dark matter associated with it. So the smallness of the dark energy or cosmological constant, being so small, demands the existence of dark matter. They're connected. They're two sides of the same coin. So string theory unifies the two theories, two subjects together. The dark energy being small implies that you should look for a dark matter. And also, this dark matter is always the one we get from these graviton waves in these extra dimensions. They're gravitons. They're gravitationally coupled only. They are weak. They're weakly interacting. Just like the experimental evidence for dark matter is only gravitational. So it fits the bill. It behaves exactly like what dark matter should be. So we would expect that there's a tower always weakly interacting and dark matter is weakly interacting. So based on these ideas, we found that the only possibility was that we have one of the extra dimensions being larger than the other one, what we call the dark dimension. So you had many other dimensions, but one of them specifically was bigger than the other ones. And so our 3 + 1 dimensional space-time that we are familiar with would live in this extra dimension, which is we can think about as the 4 + 1 dimension, with a perpendicular direction to our universe of the order of about a micron. Micron being 1,000th of a millimeter. So it's not that small, but it's micron. But that's related to the power of the dark energy itself. So if you take lambda to the -1/4, that power is fixed for us by the bounds that we get from this relation of the tower of light states. I told you that there's a tower of light states, which is the KK modes, which are these gravity waves on these extra dimensions. That fixes this exponent, and that leads to this prediction that the extra 5th dimension is correlated itself with the dark energy. So we're now predicting the existence of one more macroscopic dimension, which is relatively big, of the size of a micron. Moreover, so we can think about our universe sitting in this extra 1 micron direction. So I'm drawing only the view from the 5th dimension. You can think about our universe here like a slab of a 3-dimensional spatial slab here. if there's any temperature, if there's some heat in our universe, it will couple to gravitational waves and kind of like emits this gas of gravitons in the extra dimension. And these gas of gravitons that are generated in the extra dimension play the role of dark matter. So in the Big Bang time where the temperatures were high, if they were around the temperature of 1 GeV, the amount of matter you produce by these gravity waves from our universe, from if you wish, from the glow of the Big Bang, if you wish, in this extra dimension, these gravity waves that are generated from this glow behaves exactly like dark matter with the right abundance. So the picture emerged that we can think about our universe as sitting inside one extra dimension. So think about our galaxies as this dark slab here. This is our universe, the visible matter is there. And this perpendicular direction, which I'm calling the dark dimension, is where the excitations lead to the dark matter, like these gravity waves in the fifth dimension. So dark matter is nothing but gravity in this case. It unifies with gravity itself, gravitational excitations in this extra dimension. So the extra dimensions are becoming useful. It is precisely playing the role of giving us the rights to the matter. Yes?
How does energy conservation work in this? Because the dark matter is like a factor of 10 larger than the baryons and orders of magnitude larger than the thermals.
Yes. So the thing is that the energy first of all, the energy is not conserved in GR, that's number one. But secondly, this is generated, there's a much more phase space for generating the fifth dimension that you have only on a slab. So a lot of this was created. And you might say, wait, so original energy was in all this radiation and all that. How could the energy produced after that lead dark matter compared to the energy of the radiation today? But the way that happens is that the radiation dilutes much faster than the matter. So the matter survives after a while. So that tiny afterglow, which originally was nothing almost, becomes the dominant after a while. And that's what the matter-dominated era begins. So that feature is well known. And the reason it's more than regular matter is precisely that there's this phase space of creating them, which is not available because we cannot jump out. The regular matter cannot jump out of the slab, whereas the graviton has many, many modes. So that's the reason there's more. So if this is true, if this picture I'm saying is true, it's very radical because it will have relatively strong experimental consequences. Because if you bring, let me just go back to the previous slide. If you take 2 points on our universe and measure the gravitational force, we know that it goes like 1/r². But that's true if the distance between 2 points is large. But if you bring them closer than a micron, which is the perpendicular direction, the universe at that scale looks 4 spatial dimension rather than 3. So therefore, the force in higher dimension, instead of 1/r², goes like 1/r³, 1/r to the fourth, as you increase dimension 1 by 1. So in 4-dimensional space, the Newton's force law is not 1/r², but 1/r³. So at a distance of less than a micron or so, the force better increase. The Newton's force should get stronger and to go gradually from 1/r² to morph to become 1/r³ asymptotically. So we expect, therefore, at the micron scale, Newton's law is going to get modifications to become 1/r³. Experimental bounds today, which has measured Newton's law using Cavendish-like experiment, is giving you an upper bound. It gives you a bound that the Newton's law holds up to about 30 microns. So up to 30 microns or so, it is still 1/r². We are predicting here that if you push it down to around 1 micron, this should not be the case. And in fact, it should become 1/r³. Indeed, experiments are underway by different groups to check this statement. The experiments are being done at least 2 of them I'm aware of. One is being done in Vienna, the other one is being done in the University of Washington. And the experiment is really Cavendish type experiment. You have an attractor, which is made of this disk with panels of higher and lower mass regions, like a pie-shaped regions. And then you have a pendulum here on the other side. And as the disk rotates, this attractor, which is a rotating disk, as it rotates, when you get massive regions, one side of the pendulum gets attracted, and when the other side gets attracted, you get a vibration, oscillation of this pendulum in the same frequency as you're rotating this. And so in this way, you can actually try to measure the deviation of 1 over r squared force law. So basically, this is what I'm saying. You get this kind of experiment, and this kind of experiment is now underway. And I think the prediction is that they can at least get to 10 micron. It's not clear if they can push it much further down, but at least to 10 micron, they can do it. And we don't know if the extra dimension is exactly a micron or 0.1 micron or 10 micron, but it could potentially be in the same range that the experiments might access it in the next few years. So this is being done right now. As already discussed, it's natural to expect that some of the internal dimensions, such as the dark dimension, are not fully stabilized. There's a potential which is kind of rolling, and therefore, like an accordion, this universe is kind of opening or closing, and these extra gravity modes are also stretching with it. So the dark matter will also not be constant. It will also be rolling. So you have the energy of the universe is rolling, and the dark matter is rolling as well. This is the prediction of this model. So we put out a model in 2019 with these colleagues, basically by saying that the simplest model where you can think of this is that you have a parameter or field parameterizing the extra dimension, and the potential locally near some region in phi could be like an exponential with some exponent c. And similarly, the dark matter could be another exponent with some exponent c prime, and c prime should be order 1. So this was the prediction from string theory that this would be extremely natural to have this model. We checked this, put this into the data available in 2019, and lo and behold, we found that it doesn't quite work well. The theory seemed to want to predict the lambda CDM was a better fit at c and c prime equal to 0 with the data of 2019. So we were a bit disappointed. We had this nice model, but okay. Now, there are theoretical arguments suggesting that the average value of the exponent c, so c was the exponent, I remind you, of the potential. So the theoretical argument suggests that the average value of the c should be bigger than 0.82. We couldn't say exactly what it was, but we could argue it's not too small, given by 4 over d minus 1 times d minus 2. For c prime, the value should be order 1 up to a projection factor of cosine of theta, which means that we didn't know the direction of motion in the field space, or light direction in the field space, compared to the direction that the dark matter is elongated. In other words, whether the direction of motion is just around the dimension of the dark dimension, or there are some other sizes changing. In other words, the dark dimension, could it be just expanding like this, or it could get thinner or not? That will depend on, that will give rise to different factors up to a cosine factor. So c prime is order 1, but we couldn't say exactly what. However, there was an experimental bound for c prime. So it had already been observed that c prime cannot be bigger than 0.2. It was less than 0.2 experimentally. And that was determined because the existence of phi leads to phi itself can be viewed as approximately massless field, like a photon, but this is a scalar version. An exchange of this field between dark matter entities has a coupling which is of order c prime, and this leads to an attractive force for the dark matter. And there was already experimental bound that the ratio of this fifth force to the gravitational force cannot be too big, and this put a bound that c prime is less than 0.2. How did they know that there is a bound? The way they did it is beautiful, actually. This was done in 2000, I think, 2 or 3 by Kamiokowski and collaborator. Milky Way is here, and then you have this satellite galaxy Sagittarius, which kind of rotates around the Milky Way, and a few billion years ago was close to the Milky Way. And if there was an attractive force in the dark matter sector, then the dark matter in our galaxy and Sagittarius would attract each other more than the visible matter. So they would create a tidal force in the dark sector, displacing some of the distribution of the matter relative to the dark matter in that. And the observations show that there is not much of a disturbance. And that with a bound. And that's how they got this bound, that C prime is less than 0.2. So we know that C prime is less than 0.2. And we know that C is bigger than, on the average at least, bigger than 0.82. Okay, so this is what we know from theory. But observations still give us the best bound with C and C prime are both 0, which is the lambda CDM. Until the story changed around 2024. So in 2024, for the first time, observations begin showing that the dark energy is not a constant. Now, this caught the cosmology community by surprise, and many theorists by surprise, because it's a very simple model. You know, it's a constant, cosmological constant. Why should you make it change? In these two groups, the dark energy survey and the dark energy spectroscopic instrument experiment, one in Chile, one in Arizona, doing experiments years back and continuing actually still their experiments, they found evidence that the dark energy cannot be constant. The model lambda CDM does not quite work well with the detailed data that obtained. And so we took their data and we fit it to what we get from our 2019 model. So the discovery was 5 years after our model. So we view that as our model is kind of a model was given. The observation was done. Let's see whether our parameters, which are supposed to be order 1, how do they do? How do they fare now? So we checked this model, and we found that in our model, we get up to 4 sigma significance over lambda CDM for our model. With the same model that I was telling you about. And this we check in this paper with these collaborators. So it was quite exciting. Now that we have a prediction from string theory based on naturalness ideas from string theory, we are getting a prediction which fits the data. But now the question is, what C and C prime do we get? If we get C is 10 to the minus 10 or 10 to the plus 10 or something, that would be very bizarre. But the question is, what value for these C and C prime do we get? We have some prior what C and C prime should be from string theory. This is what we got. We found C around -1 and C prime around minus 0.05. Oh, sorry, should be a plus 0.05. Order 1, both of them. C is almost literally 1, which is, it didn't have to be, I mean, we were a bit surprised. Why is it exactly around 1 with an error of plus or minus 0.1? This is spectacular if you take into account that lambda CDM is over here. And these contours are 1 sigma and 2 sigma contours. You see how big a difference there is. So here we are with a model predicted from string theory now that this may indeed be an observation, first observation of cosmological constant evolving, which matches with string theory and predicted by string theory. Indeed, the value 1 is bigger than 0.82, which was which we expected the average value of C to be bigger than 0.82. Indeed, it is. And C prime 0.05 is less than the other bound that experimentally was found to be 0.20. Again, from totally different experiments, but that means it's not too far from being observed, perhaps, by more careful study of these tidal forces that are between the galaxies. Potentially, this could give you evidence for the fifth force acting only in the dark sector. And we find that the ratio of the fifth force a force, gravity, an attractive force among the dark matter compared to the gravitational force is around 0.5%. So 0.5% of the gravity force. Attractive force in the dark sector, 0.5% of the gravitational force is predicted, and that would be extremely interesting to check. So we're making also that prediction. These are all very exciting for string theory. The cosmological analysis of data are still continuing. The threshold for discovery is 5 sigma, not 4 sigma. And so we are not there yet. DESI is expected to analyze more data in a year or so. In fact, they're continuing till 2028. So many years of data are still going to come. It's not clear whether that will be enough to cross the threshold for discovery. But there is another observation going on by Rubin Observatory, named after Vera Rubin, who discovered dark matter in Chile, which is now collecting data of supernovae. And within less than 10 years, we should be able to know whether indeed the dark energy is evolving or not. So predictions for the future of our universe is that the rolling of the field phi is expected to continue until a dual description emerges, where you get the light tower of states, where our universe will be very different, either a large 5-dimensional one, or it contracts so much down that the extra dimension will be smaller than the Planck and some other description takes over, leading to a universe totally different from the one we live in. But that, if you extrapolate, that would take of the order of 100 billion years. So that will take a while. So let me conclude. We have seen that ideas from string theory and quantum gravity leads to a predictive unified model for dark energy and dark matter. The string-motivated model for dark dimension is currently the leading model and fitting with the cosmological models of DES and DESI. So in fact, no other proposed model by anybody currently fits the data as well as the model we're talking about. So string theory model, this simple model I told you, is the best fit model currently to the data. And we may be at the cusp of a major discovery for fundamental physics. It may end up to be a first concrete evidence for string theory. Thank you.
Does rolling also have some effect on the
Yes, so this rolling, so the field here, let me go back, oops, went back a bit too much, but let me just do it in this mode, it's okay. So you see here, matter, the dark matter grows like e to the minus c prime phi. So when the phi is rolling, the dark matter mass is changing. So indeed, if you trace back what has happened throughout the beginning of the universe till now, you find that the dark matter mass has gone down by a few percent, 2 or 3%. And this will continue changing. So yes, indeed it will. Yes?
So the potential is growing because C is minus.
Yes, so there are different epochs. There's a matter-dominated epoch, in which case the mass though goes down always, because at that time, the potential, there's effective potentials made of 2 terms. The matter density for the dark matter and the dark energy. When the matter-dominated era is dominant, means that the dark energy term is smaller than the other term. So you can ignore the V term and just talk about the rho term. In that rho term, you want to decrease rho because it wants to roll around rho. So the dark matter mass goes down. In the second region, which is the dark energy dominated era, it will depend on whether the dark energy exponent is positive or negative. In other words, whether they're aligned or opposite. The best fit data currently says they are opposite. Of course, if you try to put the same sign, you find not too far as significant. So we cannot say yet with the data whether it has to be opposite or the same. So we can have either one really. But the data fits slightly better the one which is opposite, which means that since dark energy has been dominant, the dark matter, even though the dark energy is going down, the dark matter mass is going up in the period where the dark energy has been dominant. The net effect since the beginning of the universe till now is that the dark matter has gone down net about a few percent. Yes.
My understanding is correct. There's this idea of a rolling down field also appears in theories of inflation. Is there a way to match these two ideas?
Well, good observation. So inflation theory also requires a scalar, and this scalar could be related to that if one tries to have a scalar potential. However, I have a feeling that inflation itself, it may not be the correct idea for string theory. I will explain why. It turns out that I told you that the potential has a slope asymptotically. You can show that slope is too big to allow inflation asymptotically. In fact, we have not been able to find any good model in string theory of inflation, no reliable model. People have proposed some models, but they are always in regions that we don't have strong analytic control. So we are not sure if we have been able to realize inflation in string theory or not. There are alternative ideas in string theory to realize the early universe and the effect of would-be inflation, which involves homogeneity and solving the horizon problem and all that. There are other solutions having to do with string dualities that I mentioned briefly, but I won't have too much time to describe it. It takes another lecture if I want to describe that.
Target dark matter that you proposed, is it reconcilable with the recent observations of potential cosmic birefringence?
Current observation of what?
Cosmic birefringence.
There's no contradiction with that, yes. There's no problem with that. So there are bounds for the dark matter changing, but the bounds are 5% or something of the net dark matter changing of the mass and so forth, and those pictures are consistent with this. Yes.
And also many cases of compactification, which doesn't support probably those parameter ranges. Was the non-perturbative effects to like different solutions are considered? Or no?
Well, good question. So let me explain. We did not construct a string model here. I did not tell you what is the shape of all of these extra dimensions, etc. What we did was to basically abstract from string theory certain principles and applied them. So these values for C and C prime are generic. So C being order 1 was a prediction we made because of all the string models. Now, you could be at the top of a, for example, potential, in which case C is 0. It could be accidentally there. But typical values of order 1. So therefore, I would say that we were just using naturalness in string language, and that's where we assumed, and that's what we were getting. So it fits beautifully with string naturalness.
I might be misremembering, but in addition to the dark energy being non-constant, wasn't there some indication from Desi that there might be some issues with single field scalar models because there was like some region where the equation state was less than -1?
Excellent question. So for people who are not familiar with the question, so let me explain what the question is about. So there's this quantity called W, which is defined as the pressure in the dark energy, for the dark energy, divided by the density of the dark energy. So the pressure over the density, that quantity, is called W. If the theory had cosmological constant, if the dark energy was constant, P and rho are equal except opposite sign. So P is negative, negative pressure is exponentially expanding, and you find P over rho is exactly -1. So W equals to -1 is the constant cosmological constant situation. Now, Desi team did not want to assume W is -1, the team that they were doing this experiment, but they didn't have any theory a priori. What theory should they match? They didn't want to bias themselves. So they said, you know what? We measure the value of W and how W behave with redshift, as you know, when you go back in time. And they put the value of W now, we call it W0, and the slope they call WA. W0 and WA was the value of W now and the slope. And they said, let's measure that. And they found the value of W0 and WA with the slope. So they found the profile for W0. Let me see if I can find the chalk here. Yeah. So they found the profile. If you plot W as a function of redshift, which is now here, -1 is when you have a cosmological constant. They put it to a linear, some kind of a model, which is basically the value now and some kind of a slope, and they found some trajectory like that, where z is around 0.5, it crosses the -1 line. That's what they fit to their data. And the thing which was strange about their model was that it crossed this line. It turns out anything below this line is theoretically impossible. That's what's called the phantom regime. But their data from the sky was giving us is that you're getting there. So theorists were screaming at them, you're doing something which is not allowed. What are you getting? Okay, so that's the reason he's asking the question, what about that behavior? They were getting this crazy behavior. It turns out that the reason they were getting this crazy behavior has a simple reason. They were assuming, what were they trying to compute? They had defined W as the pressure for the dark energy divided by the density of dark energy. But to compute the density of the dark energy, the way they computed it in their experiment was to take the total density in the universe, which they can easily see by the expansion of the universe, and subtract the portion which is coming from the matter. But they assumed the matter portion scales like the length cubed of the universe. They assumed the dark matter was constant in mass. And they fit it to the data, and they get this crossing. In our model, dark matter mass is not constant. However, you can take our model and subtract rho of m at some particular value of the redshift, and then fit it, and then see what you get. You get exactly this phantom-like behavior from a perfectly fine physical model. So a perfectly fine physical model gives you this behavior if you define W in this silly way. Because rho of you cannot decouple the dark energy and dark matter, they're coupled. But if you insist it, you'll get a crazy answer.
Other questions?
Now that you have this model and that experiment are on the way, what are you going to be working on?
Why this is going on?
No, what are you going to be working on? What is like your next project?
I have many projects, not some of them not related to this, even though this is super exciting. I'm doing some projects related to this. I will tell you a few more things, perhaps. The dark matter I told you about is this tower of gravitons, but they turn out to decay among each other. So in other words, the tower mass goes down in a different way as well. Whereas, so there are two effects. One is the decay among each other in between the elements in the tower. And when this happens, it turns out one of these KK modes, these gravity modes, decays to a pair of them, giving you a kick to the dark matter. So our model predicts that dark matter is not just sitting around, but actually occasionally gets a kick dividing into two pieces, like one of them splits to two pieces with a kick, with the velocity something around 10 kilometers per second or so. We don't have an exact figure. But when this happens, if you have dark matter clumped, say near the center of the galaxy, they'll be kicked away. So you expect that they're near the core of the galaxy, where they are not moving anymore, the rotation velocity is zero, you will find that they should be void because they will be kicking away by some kick velocity. And so you expect that the dark matter will deplete the center of galaxies. Indeed, there is what's called the core cusp problem in galactic formation, which happens to be that there's a puzzle that the dark matter density near the core is less than it's supposed to be. If you assume that dark matter is just constant dark matter. So that's called the core cusp problem, and cosmologists are aware of this problem. They have tried to propose solutions of it involving stars and what they call baryonic physics. But we think the solution might actually have to be doing this feature of exotic dark matter, which has this kick velocity portion. So that's one project we're working on. And there's another version of this project we're working on here. We assume that the extra dimension, as it's expanding, the universe has this extra dimension has the same volume. The volume doesn't change, but it may have changed. Why they assume it's not changing is that they simplified our analysis. But if you allow the volume of this extra dimension to change, it implies Newton's constant should also change. So it's not too far from this model to allow Newton constant to gradually change of the order of a few percent. And that's some other thing we are studying, whether or not that's consistent or whatnot. But those are among the possible cosmology models I'm studying with our colleagues. There are a few questions here. There's, I think these hands were up. I'm happy to take any questions, but you put the upper bound for time. Well, the people might want to leave, so I don't want to insist, but you decide the time. Yes.
So then either way to adopt the models like for the galaxy, like replacement for the NFW profile.
For what profile?
Then either way to adopt your dark matter profile from your model.
Yes, so we are running such simulations precisely to find for halos, what kind of profile for dark matter we get. We are doing those simulations. Well, we are not yet, I wish I could share, but actually Kamiansky et al. Have done, and they have shared their codes. I think for spherically symmetric such dark matter profiles. So one could also use that if you're trying to start working on such models. Yes.
So I would suggest that in the spirit of the time, we thank Cumrun for our lecture.
Yes.
And then any other questions can start as well.
Thank you very much.
Size of